VCE Chemistry, Unit 4, Chapter 11, the Physical Properties of Organic Compounds. In this session, we'll mostly discuss boiling points, viscosity, and flash point, because all these three properties come down to the intermolecular forces between molecules in the same organic compound. Okay. So the study design requires us to be able to explain the trends in physical properties with reference to structure and bonding. That means basically you need to refer to what kind of intermolecular forces are there in that particular compound. Okay? So in your written responses, make sure you hit the following 3 points. Functional groups or general structure that leads to that particular intermolecular force. And what is that force that determines one of the physical properties? And basically, stronger forces means higher boiling point, higher viscosity, and higher flash point. Now let's look at them one by one. So before we dig into it, let's revise the definition for homologous series. That is compounds that are a member of the same homologous group, basically methane, ethane, propane, butane, pentane, hexane, or anything, we call them alkane. So whenever we are saying alkane, we are basically referring to that alkane homologous series. Okay, so homologous series have similar structures. They have similar chemical properties because they have the same functional group or groups. Okay. They have the same general formula, that is for straight chain alkane, that's CnH2n plus 2, or for cycloalkane or alkene, that will be like CnH2n. Okay. And then, but when it comes to physical properties, compounds in the same homologous series do not have the same physical property, but they do demonstrate a pattern, either increasing or decreasing or remain the same but not exactly the same physical properties. Okay, so for example, when it comes to solubility, for our homologous series of carboxylic acid with only one carboxyl group, you will see that as the chain gets longer and longer, they're still in the same series, but the solubility decreases as the number of carbon atoms increases. Okay, so similar structure, similar chemical properties, same general formula, but different physical properties. They're either increasing or decreasing. Okay. So boiling points. Trends, when it's within the same homologous series, then the only difference between molecules in the same series is that the chain length, basically the amount of CH2 a molecule has, right? Chain length, so longer chains will result in higher molecular mass, which will result in increasing dispersion forces. Now, how do you do this in the written response? A sample question might ask you, explain why octane is liquid under room temperature when methane is gaseous, with reference to bonding and structure. Okay? So your response should be, first of all, methane and octane, boiling points are determined by dispersion forces. This is what I mean by you go from structure, methane, they're octane, and they're alkanes. So alkanes' boiling points are determined by dispersion forces. So you have identified the intermolecular force that's responsible to boiling points. Right? Then dispersion forces increase as molecular size increases. That's your knowledge of what determines the strength of dispersion forces. Then, as a result, leading back to the question, then octane has a higher boiling point and therefore remains as a liquid under room temperature. Okay? Now, we actually have learned about one case of applying difference in boiling point in chemical production. That is called fractional distillation. That is this tower. So if you still remember from year 11, this is a tower used to separate the components of crude oils. So we heat from the bottom, and then as you go up, the temperature of the tower decreases. Okay, so if you heat at the bottom, the bigger hydrocarbons, because they have really high boiling point, they will remain as liquid at the bottom, even if you heat it. But the smaller molecules will vaporize under high temperature, and therefore rise up to the top. And once they go to the top, because the temperature decreases as you go up, then they become liquid again, and therefore being collected. So at different heights along the tower, hydrocarbons of various chain length are collected separately. Okay, so this is an application of boiling points. So the trends in boiling points between different functional groups will be determined by what functional group there is, because different functional groups will result in different type of intermolecular forces. So this is what we're talking about, not just dispersion forces, but also H bond and dipole-dipole. Okay. So we have to determine case by case. So normally the more polar the functional group, the higher boiling point. More polar functional groups can make dipole-dipole or hydrogen bond in addition to dispersion forces. Okay? So basically, in general, if we have examined the particular type of intermolecular forces that can happen between different molecules, we can arrive at this general trend. So for molecules of similar size, this is in an effort to rule out the effect of dispersion forces. So when dispersion force is not at play, normally we have carboxylic acid have higher boiling points than alcohol, then ester, ketone, or aldehyde, and then larger than hydrocarbons. Let's have a look. So this is a summarize of the trend. But first of all, we notice that since all molecules have dispersion forces, the general trend still fit here. So the longer the chain, the bigger the molecule, the higher the boiling point. So for each category of the compounds, the same trend observes. And then from the top, you have carboxylic acid, followed by alcohol. So because both molecules have a hydrogen bonded straight away to the oxygen, so that hydrogen can form hydrogen bond with another molecule. Okay, so because of the hydrogen bonds exist in carboxylic acid and alcohol, they will have highest boiling points. But you notice that carboxylic acid is still higher than alcohol. That is because carboxylic acid can form dimer due to its molecular shape, and therefore you're basically increasing your molecular size by merging two molecules into one. So therefore, carboxylic acid still has higher boiling points than alcohol. Then somewhere in the middle you have ester and ketone. We don't have aldehyde here, but even if you have aldehyde, it will be along somewhere in the middle. Okay, so ketone and ester, they have oxygen atoms in their functional group. However, they do not have a hydrogen directly bonded to the oxygen. As a result, those oxygens only just make the molecule more of a dipole molecule. So the intermolecular force that determines the boiling points in ketone and ester and aldehyde would be dipole-dipole force. Okay, so they're somewhere in the middle. And then you have all the hydrocarbons at the bottom because they only have dispersion forces. Okay, all the other molecules have dipole-dipole and or hydrogen bond in addition to dispersion forces. Therefore, hydrocarbons normally have the lowest boiling points. Okay. And when it comes to alcohols, we talked about there are different types of alcohol. So from primary to secondary to tertiary alcohols, the environment around the hydroxyl groups gets more and more crowded. So primary alcohols have the hydroxyl group at the end of the chain. And secondary has it in the middle of the chain, but that carbon is okay. It's still sort of just in the middle of a straight chain. Now, for tertiary alcohol, that hydroxyl group is on a carbon that also has branches. Okay, not just in the main chain, but also has branches. In that case, that hydroxyl group is really crowded, things around the hydroxyl group. So the presence of alkyl group around hydroxyl restricts a molecule's ability to form hydrogen bond because it's harder to reach for other molecules, because it's really crowded. And therefore, under similar conditions, when you have same number of carbon atoms, tertiary alcohol has the lowest boiling point, while primary alcohols has the highest boiling point.